All right, this is section 14.5, video number 2. So now we're going to get into a little of the application. This next problem, I always kind of giggle because for whatever reason, this just is the common problem with this particular author. You get this problem about a bug's path. Not really sure why. But it says the temperature at a point xy is T of xy, measured in degrees Celsius. A bug crawls so that its position after t seconds is given by the parametric functions that you see there, where x and y are measured in centimeters. The temperature function satisfies t sub x, or the partial of t with respect to x, at 2,3 equals 4, and t sub y, or partial of temperature with respect to y, at 2,3 equals 3. How fast is the temperature rising on the bug's path after 3 seconds? So, not exactly sure what's going on here. The bug is crawling, I guess, along some kind of an XY plane, or something that we're at least going to call an XY plane. You know, however the bug's moving, he's moving in all kinds of different directions, wherever the bug is. And after 3 seconds, wherever that is what we're trying to figure out, how fast the temperature is rising on the bug's path. So we're trying to find the change in temperature along the bug's path, which is given by t. So our dependent variable is temperature. That depends upon both x and y, which both depend upon t. So x and y are going to be our intermediate, where t is the independent. So we can find a full partial derivative, in this case, excuse me, a full derivative of t with respect to t, of all things, dt over d little t. So it's going to be partial with respect to t, excuse me, a partial of capital T with respect to x times the full derivative of x with respect to t, plus the partial of temperature with respect to y, its y position, times the full derivative of y with respect to time. So that's what we've got going on here. So just so we can kind of label some of this stuff, this is how fast the bug moves left or right. How fast the bug moves left or right, basically the horizontal movement. This one, you would think, is how fast the bug moves vertically, or up and down. This is the change of temperature horizontally. Change of temperature horizontally, where this one is the change vertically. Change of temperature vertically. All right, so now that we have at least all of that, we can start piecing this together. So let's see, what do we know? We know that the t sub x at 2,3 is going to be, well, it says that it's 4. So that actually makes that easy. So the derivative of temperature with respect to x is 4. So that's the first part. Times the derivative of x with respect to t. Well, that's going to be, let's see, that's going to be 1/2 1 plus t to the negative 1/2 times the derivative of the inside, which is just 1, plus the derivative of t with respect to y, that's this piece, that's going to be 3, they gave us that information, times the derivative of y with respect to t, which is just 1/3. So the only thing I have to figure out is t. Don't really have to figure it out. They gave that to me. It's 3 seconds, so we can plug that in. If we didn't necessarily know the value of little t, we could figure it out, because this right here represents your x, that represents your y, that represents your x, that represents your y. So if I were to plug in, just for example, 2 here for my x, I could find the t value, square both sides, subtract the 1, and you would get t equals 3. Or you could plug in 3 for the y value and solve that for t. Subtract 2, multiply by 3, you'd get t equals 3. Either way would still work. In this case, we didn't really have to find that. T was given to us as 3 seconds. So now we can just simplify this. So that's going to be, 4 times a half, which is 2. Plugging the 3 in for t, we get 4 to the negative 1/2 plus 1. 4 to the negative 1/2 is going to be square root of 4 is 2, but flipped over as a half. So 2 times a half is 1. 1 plus 1 is 2. And it is going to have units. So we are talking about how fast the temperature is rising on the bug's path. And it's going to be with respect to time. So it's going to be in degrees Celsius. I think it was Celsius, or was it Fahrenheit? Degrees Celsius per second, I believe it was. So at the specific time, t equals 3 seconds, the temperature on the bug's path was rising at 2 degrees Celsius per second. What exactly that means, I don't know, but that's what it was. All right. Example number 7. This is going to take a little bit of time. We got 3 different parts to do here. The length L, width W, and height H of a box is changed with time. So all of those change with time. At a certain instant, the dimensions are L equals 1 meter. M, I was trying to figure out why I put the M there. 1 meter. And W and H both equal 2 meters. And L and W are increasing at a rate of 2 meters per second, while H is decreasing at a rate of 3 meters per second. At that instant, so at the very instant when those measurements are L equals 1, W and H equals 2, at that instant, find the rates at which the following quantities are changing. So we want to find out how the volume is changing, how the surface area is changing, and how the length of the diagonal is changing. All right, so let's list our stuff. We know our dependent variable is going to be volume. That's for the first one. Our intermediate variables are going to be L, W, and H. And our independent variable is time, T. All right, so to do this for volume, first thing I guess we need is the equation for volume, which is just length times width times height. So the the full, it can do a full of V because I only have one independent variable with respect to time is going to be the partial of V with respect to L times the full of L with respect to time plus the partial of V with respect to W times the full of W with respect to time plus the partial of V with respect to height times the full of height with respect to time. And I believe that we have all this information. Let's see. Partial of V with respect to W is going to be LH. The full of L with respect to T. That's just given to us. Where is that? L and W are increasing at a rate of 2 meters per second, so that's 2. Plus, the partial of V with respect to W is going to be, I did that wrong, sorry. First one is with respect to L, that's going to be WH. This one, the partial of V with respect to W is LH, times the derivative of W with respect to T, which is also 2. The partial of V with respect to H is LW, times the full of h with respect to t, that one's 3. Okay, now we can just fill all the rest of this stuff in because they gave me all the values of L, W, and H. So W and H are both 2, so that's 2 times 2 times 2, which is 8. L and H are going to be 1 times 2 is 4. And L and W are going to be 1 times 2 times 3, so that's 6. So we should get 18, and let's see, what is this? This is volume, so it's going to be meters cubed per second. So there you go. Part B, surface area. Okay, dependent and intermediate independent variables, all the same. So all we need to do is, except for in this case, dependent variable is going to be surface area, so SA. We need the equation for the surface area. This is a box. Okay, so you're going to have 6 sides of the box. You're going to have one side, which is the length times the width of the box, which of course is going to be doubled because you've got 2 of those. 2 length times widths. You're going to have 2 length times height, and you're going to have 2 width times height. So basically, let me kind of sketch this down here just to make sure everybody's kind of with it here. So we've got some kind of a box. Try and make it so all these dimensions are slightly different. Something like that. So we're going to say that we've got a length, a width, and a height, and you're going to have 2 of every face. So like the length times the height is this face right here. The width times the height is the front face right here, and then the length times the width is the top of this box. Hopefully that makes sense. Okay, so let's go back to our problem. So if we want to get the full derivative of surface area with respect to time, that is going to be, let's see, the derivative of the surface area with respect to the first variable, L, times the full derivative of L with respect to t, plus partial of surface area with respect to the width, times the full of the width with respect to t, plus partial of the surface area with respect to height, times full of the height with respect to t. All right, let's see what we get. Derivative of the surface area with respect to L is going to be 2w plus 2h. The last term is gone. Okay, the dl dt, we kind of already have that from the top. That was 2. I'm just copying it from the one above, to be honest with you, so I don't have to scroll up and down. Derivative of surface area with respect to w is going to be 2l. The second part is gone, plus 2h. Derivative of w with respect to t was 2. Derivative of surface area with respect to h, first part is gone, and we're going to get 2l plus 2w, and dh over dt was 3? Yeah, 3. No. Yeah, dh over dt was 3. Sorry. Okay, so now let's fill this stuff in. Shoot, now I'd have to go back and remember. W and H were both 2, L is 1. So if W and H are both 2, we're going to get 4 plus 4 is 8 times 2 is 16. And the second one, L is 1, so that's going to be 2 plus 2 times 2 is 4, so 2 plus 4 is 6 times 2 is 12. And then the last one, 2 plus 4 is 6 times 3 is 18. So adding all that stuff up, 30, 46, I believe. Something's not right. Oh, I made a mistake. I made a mistake on the one above, too. Hopefully you guys caught it. I think I caught it in time this time. Forgot that part. h is decreasing at 3 meters per second. So that means that this was a negative 3, which means that this was a negative 6, which means that we should have had 12 minus 6, so that's 6 meters cubed per second. My mistake. So then that's going to be a negative 3 there, which is going to make that a negative 18. So then we're going to get 10. And it's surface area, so it's meters squared per second. So the surface area is increasing at 10 meters squared per second at that very instant. And then the last part. Sorry about that mistake. I'm glad I caught it this time. Okay, now we want to talk about the length of the diagonal. Length of a diagonal of a box. Let me see if I can kind of draw this in there. So the diagonal of a box is going to go from one corner, say right here, the lower left corner, to the upper right corner up over there. So that diagonal is going to look something like that. Not exactly easiest thing to draw to at least give you the idea, but that's what it is. So in order to do this, we actually need the equation for the diagonal of a box. Well, the diagonal of a box is literally going to be like the Pythagorean theorem, except that it's three-dimensional. So the diagonal, whoops, let's go back to orange. Diagonal of a box is going to be the square root of L squared plus W squared plus H squared. Okay, and you can actually go back to previous lessons to see that that's how that one works out. Basically, you almost want to treat this like it's your origin, and then this point up here is like your L, W, H, your length, width, and height point. So the distance between those two things is just the extended Pythagorean theorem in 3 dimensions. Okay, so now we want to find the full derivative of the length. Ooh, let's use a capital L for length. Or no, let's just use for diagonal. We'll call it DD. How about that? With respect to time. So that's going to be the partial of D. Oh, this is going to get confusing. Over the partial of L times the full of L with respect to time, plus the partial of D with respect to W times the full of W with respect to time, plus the partial of D with respect to H times the full of H with respect to time. Okay, so the derivative of D with respect to L. The good thing is it's going to be the same derivative when we do these the partial parts, with the exception of the numerator. So the first one I'm going to write out. That's going to be 1/2 the whole thing on the inside to the negative 1/2 power times 2L. So that's the only part that's going to change. This part right here is the only part that's going to change. The rest of it will be the same the whole time. And then we have the partial of L with respect to T. Again, we did that above. The partial of L with respect to T was 2. Okay, the derivative of D with respect to W, once again, it's all of this, so that doesn't change. So it'll be 1/2 that whole thing to the negative 1/2. I'm being lazy and not writing it out, times 2W. And then the partial of W with respect to T was also 2. Plus 1/2 that whole thing to the negative 1/2 times 2H. And the derivative of H with respect to time, I remember this time, is -3. So now let's go ahead and figure out what one of these parentheses is, and then we should be able to simplify this pretty quickly. So L squared plus W squared plus H squared. So L, let me remind myself, L is 1, W and H are 2. So that's going to give me 1 plus 4 plus 4, so that's 9. The square root of 9 is 3, but it's to the negative power, so it's a third. So that's going to give me 1/3. These 2's and the halves are going to cancel out. Let's get rid of those, make everything a little bit easier. So that's going to be a third. Whoops, go back to orange. That's going to be a third, and that's going to be a third. So now we just got to fill the rest of this in. Again, L was 1, so that's going to be times 1 times 2. W was 2, so that's going to be 2 times 2 is 4. And H is also 2, so that's going to be 2 times -3, which is -6. So we're going to get 2/3 plus 4/3 minus 6/3, which ironically is 0. And this is length, so it's going to be 0 meters per second. So what that says is that I guess the length, the width, and the height are all changing in such a way that the diagonal actually isn't changing at all. The length of the diagonal is staying the same, even though the box is changing. But that's because 2 of the pieces are expanding, the other one is shrinking, so the diagonal could stay the same. That's a pretty interesting result. All right, one more example to go. And this is kind of a tabular one. It's got like a chart to deal with. So we just have to kind of define the pieces here. So suppose f is a differentiable function of x and y. Oh, I can already see a mistake that I made here. That should be g of x, y. Equals, actually, that should not be g of x, y. It should be g of u and v. G of u, v is defined as f of e to the u plus sine v. Nope, I had it right the first time. That's x and y. Sorry about that. F of e to the u plus sine v, e to the u plus cosine v. Use the table of values to calculate g sub u of 0, 0 and g sub v of 0, 0, or basically the partial of g with respect to u and the partial of g with respect to v. Okay, so this is what we know. G is a function of x and y. So g itself is your dependent variable, where the intermediate variables are x and y, and the independent variables, in this case there's multiple of them, are u and v. So at least we can do is set these things up. So we know that and it's going to be partials. The partial of g with respect to u, we got to do this with both, is going to be the partial of g with respect to x times the partial of x with respect to u, plus the partial of g with respect to y times the partial of y with respect to u. Okay, that's the first one. And then we know we're going to have to do the partial of g with respect to v, which is the partial of g with respect to x times the partial of x with respect to v, plus the partial of g with respect to y times the partial of y with respect to v. So now we need to figure a couple of things out. First of all, this right here is the partial of u with respect, a partial of g with respect to u. Okay, these are actually your u and v values. Same thing over here. These are u and v values. This is the partial of g with respect to u. So we're trying to find these partials when u and v are 0, 0. Okay, so we know But since u and v are 0, 0, we can figure out what x and y are because I can plug 0, 0 into the f function and figure out what g of x, y is. So let's figure out the x and y values. So this part here represents x. This part here represents y. So let's see. E to the u plus sine of v equals x. So if I plug 0 and 0 in for u and v, I'm going to get 1 plus 0 equals x, or x equals 1. Okay, that's important. Do the same thing for y. So we're going to get e to the u plus cosine v equals our y value. Plugging in 0 and 0 there, we get 1 plus cosine of 0, which is 1. So y equals 2. Okay? So now let's see the parts here we're going to need. We got the partial of g with respect to x. The partial of g with respect to x. Well, let's see. Partial of g with respect to x. So the partial of g, which is defined as f with respect to x, so it's really f sub x, this one right here, whoops, this one right here, at the point where x and y are 1, 2. So it's this column right here, so that's going to be 2. Partial of g with respect to x is 2, and good thing is that's 2 in both cases. The partial of x with respect to u. Well, that's the derivative of this piece with respect to u, and that's just going to be e to the u, evaluated at 0, 0, because that's your u and v values. So if I plug 0, 0 in, 0 in for u, I'm just going to get 1. Okay, that doesn't apply to the next part. Partial of g with respect to y. So now we're talking about f sub y at 1, 2, which is 5. Okay, that will apply to both pieces. Put a plus sign in there. And then the partial of y with respect to u, that's the derivative of this one with respect to u, and that's just e to the u. Again, plug in your 0, 0 because those are your u and v values. So you get e to the u, or e to the 1, excuse me, e to the 0, excuse me, is 1. So our first one, we're going to get 2 plus 5, which is 7. Okay, now we just have to figure out for the second part. The second one, we want the partial of x with respect to v. So now we're taking the partial of this piece with respect to v, and that's cosine of v. Again, evaluate that at 0, 0, because those are your u and v values. So cosine of 0 is 1. And then the partial of y with respect to v, that's this one right here, is going to be negative sine v. Again, plugging in 0, 0, negative sine of 0 is 0. So in this case, we get 2. Okay, not the easiest one to do with the table. You got to kind of go back and forth and figure out which variables are what. Super long video, but I only did it in 2 videos in order to keep it just down to 2. So that should be plenty enough for the chain rule. We should be good.